Okay. So... Alright, hello, everybody. How's everybody doing tonight? I hope everybody is doing absolutely fantastic. I hope everybody's doing well. I hope everybody is doing well tonight. Hopefully you are doing good as well. Yes. Thank you very much for coming on out here to the stream once again. All of you are absolutely fantastic. How's everybody doing today? Trying to still get things kind of squared away. I got a new microphone, so been kind of trying to balance things out here with my volume settings to some degree of success. So there's that. All right, wait for some people to come on in, and then we'll go ahead and get started here momentarily. So we got a little bit of a late start, but that's okay. Hello, everyone. There we go. There we are. There we go. We got here today. See a few people in there in the chat already. Hopefully you all had a absolutely wonderful weekend. Had a nice time. I sincerely hope you did. Hopefully you had a nice relaxing day. I'll wait for... Oh, let's see. We've got a few more people to come on in because I know I started a little late. Yeah, I did that. Yeah, that's fine. Alright. Good stuff. Alright. Get a few more people in here. Nabs the vibes. There you go. Alrighty. Maybe they're watching. Hello. Let's see if you're there. No? Okay. That's fine, I guess. Alright. That's fine. Okay. There we go. Alright. So, we're gonna go ahead and get started here for today. Let's do some intros, ladies and gentlemen. If you're there, we're just gonna go ahead and start the lecture here. Hopefully we'll get a few more people coming in. But if you're there, then we're just gonna start. Okay? Alright, let's do it. Okay, let's get started today! Alright, welcome back, everybody. Welcome back to Tuesday. Hope you have a nice weekend. Alright, so for today, ladies and gentlemen, today we are going to be moving on in Chapter 5. Okay, so we did the last section here of Chapter 5, Section 5.4. We talked about, again, another rule here, the multiplication rule. Today, we're going to be general multiplication rule with conditional probabilities. Today, we're moving on to the last section of Chapter 5, and primarily what we're going to be doing here today is we're going to be talking about counting, okay? So counting is going to be what we are discussing here today. And of course, discussing about how to count within probabilities, and then of course finding probabilities after we use this said counting. All right, so what exactly is counting here? Well, counting, of course, is not the conventional sort of counting, is not what we're talking about here. You could talk about counting 1, 2, 3, 4, 5. But what we're specifically counting here in this case, and in this section, is going to revolve entirely around how we can count the number of ways to do a particular task. So if we talk about the number of ways to do a particular task, okay, that's the thing that we want to count, and then we're going to look at it from 2 different points of view, okay, and that is in relation to permutations and combinations. So let's go to the big board here, and let's take a good look here at the handout. All right. So here's our handout just right here. All right. No problem. All right, so let's talk about what we're going to be going over here today in section 5556. All right, so objectives here, we're going to solve counting using the multiplication rule. Again, using permutations and combinations. Permutations of non-distinct items, we'll talk about that at the end of the class here. And also compute probabilities using the permutations and combinations. That's going to be a little bit more important at the end. All right, so we'll discuss about that and put hopefully 2 and 2 together. All right, now let's go ahead and take a look here at number 1. Okay, so exactly how do we count here in these circumstances? Let's look at number 1 here. So what is the fundamental principle of counting? Okay, so that's the first thing here. What is the fundamental principle of counting? So it basically says, if a task consists of a sequence of choices in which there are P selections for the first choice, Q selections for the second choice, R selections for the third choice, and so on, then the number of ways that that task can be done is done by P times Q times R times ... number of ways. Now, as it stands, it's pretty abstract because you got letters kind of thrown in there, you're multiplying stuff with each other, that sort of thing, and that's perfectly understandable if it looks confusing at first. But let's go ahead and do a practical example here, and let's see how we can actually apply this fundamental principle of counting, okay, in a realistic example here to figure out how many ways we can do a particular something. All right. So the example that I'm going to use here in this instance is, let's go ahead and say we are in an ice cream shop. Okay, so we're going to go get some ice cream. All right. Now, on this ice cream cone or in this ice cream bowl, whatever you want to call it, all right, let's say we want three scoops, okay? We want 3 flavors of ice cream. 3 scoops of ice cream, we want 3 different flavors. So each flavor has to be different. All right, so we want to, we're in the mood for variety. Has to be different. So, now let's say the number of flavors in this particular ice cream shop, we have 20 flavors. Okay, so we have 20 flavors overall of which to select from. All right, and we want 3 of them here, and they have to be different each time down. Okay, so let's draw our little pictures that we've been kind of doing here throughout this chapter into determining how many ways can we construct an ice cream cone with 3 different flavors, or an ice cream bowl, whatever you want to call it. Okay. So, let's see if some of you are out there here. So, first and foremost, let's get the first scoop down. Okay, so I order for my first scoop that says, okay, which flavor do you want? Now, here's the real question. How many choices do I have for the first scoop of ice cream? How many choices do I have for the first scoop of ice cream? Okay. I have exactly, okay, good. So I have 20 choices, right? I have 20 different flavors, so of course I have 20 choices for my first scoop. All right, so I picked my first choice. It could be my favorite of mint chocolate chip or vanilla. Maybe for you it's cookie dough. I don't know. Whatever. It doesn't matter. But you have 20 choices at the end of the day. So you pick your favorite first choice. That's fine. Let's say person asks, okay, what's your second choice? What's your second scoop going to be? And your second scoop has to be different than the first scoop. So how many choices do you have for the second scoop then? How many choices do you have for the second scoop? Okay, Strolling Bill says 19, and same with Maritza. Okay, good. That's correct. That's right. So we have 19 choices for the second scoop of ice cream. All right, that's fair. Definitely fair. All right, so now let's use just logic here. Third scoop of ice cream. How many choices do we have now? How many choices do we have now for the third scoop of ice cream? All right. So for the third scoop of ice cream, we indeed have 18 choices for the third scoop. Okay? So we can't use the same flavor as we did the first two. So again, that means we have 18 choices for that third scoop, since all of them have to be different. Okay, now what I would like you to do, of course, is to multiply 20 times 19 times 18, and we're going to see how many ways we can put together 3 unique flavors of ice cream, all in the same cone. So can anybody do that for me? 20 times 19 times 18. What's that going to be? All right. Very good. 6,840. Nice. All right. So there are 6,840 ways to get 3 scoops of different flavored ice cream, contingent on there being 20 different flavors. Okay. Seems pretty reasonable. All right. Now, before we move on, are there any questions about that? Any questions? Hopefully that was pretty straightforward. Again, type no in the chat if you don't have any questions. If you do, then ask. All right. Good stuff. Okay. Let's go ahead and move forward. All right. Okay. So let's say, for example, guys, let's say there was another way to kind of figure this out. Now, admittingly, this is the easiest way to figure this out because we just logicked our way through this, okay? We logically looked through this one piece at a time, said 1 scoop, 2 scoops, 3 scoops, and we were able to find how many ways we can express 3 scoops of different flavored ice cream, 6,840 ways. But let's take a look at a different way of looking at it. Again, I'm going to replicate the same results here, but maybe just use it for more broad general problems as well. All right, now in order for us to do that here, let's take a good look here at number 2. We're going to need a little bit of build-up in order to get there. So let's look at number 2. Number 2 says, what is factorial and its notation? So first of all, let's talk about factorial. Factorial's notation is exactly as you see here on the screen. It is by this exclamation point, so that is not a mistake. That exclamation point is the notation for a factorial. And so if we write n factorial here, that's equal to n times n minus 1 times n minus 2 times ... all the way down to times 3 times 2 times 1. So basically, at the end of the day, we have a bunch of whole numbers that we're multiplying with each other all the way down to 1. Okay, so as you can see there down at the bottom, what would 5 factorial look like? Well, that would be 5 times 4 times 3 times 2 times 1. Multiply all those together, and you get 120. Okay, so that's essentially what you get there. And we have a very special property here for factorials that is used sometimes, and that is 0 factorial here is equal to 1. So some problems, a lot of problems sometimes use 0 factorial as part of the process. So again, if you do see that, or you have to encounter that or use that, yeah, that's going to equal 1. It's just a unique property here of factorials that we use from time to time. All right. Now, where are we actually going to be using these factorials here? How is this going to help us here in, say, a problem like we just did here in this previous example? Let's take a look at number 3. Okay. So number 3 says, what is a permutation? So a permutation is the number of arrangements of R things chosen from a pool of N things where order matters. And here's the notation that you see here on the screen. So the permutations here would be NPR. So N here would be, again, the total number that we have out of R things. So N would be the total pool, R would be what we're choosing from. And that's going to equal N factorial over N minus R factorial. Okay? And this basically says that repetition is not allowed. Okay? A repetition is not allowed. Now, like our previous example here, why is in our previous example is permutations happen to be the most applicable thing that we can do here? Because that's exactly what's going on here. Why is permutations actually our guy here to really define? Well, because of the fact that I insisted that in this previous example that every scoop that we were going to choose has to be different. And because it has to be different, suddenly order does matter. Because if I do the first scoop to be, say, again, vanilla ice cream, well, then I'm not allowed to use vanilla again for the other 2 scoops of ice cream. Okay, so order actually significantly matters because it takes away one option off the table every time you go down the line. So, in this instance, what we would do is we would go ahead and say, okay, well, we have 20 flavors of ice cream, and we're going to permute. How many are we going to permute? We're going to permute 3 of them because we're selecting 3 flavors like we had from before. Now, if we apply the formula here, like you see off to the left, this would be equal to, let's go ahead and do this out here. This would be equal to 20 factorial divided by 20 minus 3 factorial. So again, we get 20 factorial divided by 17 factorial. We do 20 minus 3 first. And then we go ahead and what you can do here is you can actually figure this out by hand. I'll show you how we get 20, 19, 18. You get 20 times 19 times 18, but if you go to 17 here underneath factorials, basically you do 20 times 19 times 18 times 17 times 16 all the way down to 1. So we could just put in 17 factorial because you're just multiplying stuff from 17 all the way down to 1. And so we have a 17 factorial on the top and on the bottom. This is basically how it's designed. And then as you can see here, what's left over, we have 20 times 19 times 18, which is exactly the same 6,840 that we have from before. Okay? Any questions about that so far? Nope. All right. Okay. So, let's take a look at another example, and let's see where we can also apply this here. So we're going to do number 47 in the textbook here, and we'll showcase how this works. All right. Come back to that. Here it is. All right. Let's look at 47. All right, so 47 is forming a committee problem. So 4 members from a 20-person committee are to be selected randomly to serve as a chairperson, vice chairperson, secretary, and treasurer. The first person selected is the chairperson, the second the vice chair, the third the secretary, and the fourth the treasurer. How many different leadership structures are possible? Okay, we're trying to find out the number of leadership structures that are possible underneath this this process. Okay, now the real question is, in this case, for number 47, does order matter in number 47? Does order matter in number 47? Yes or no? Does order matter in number 47? Yes or no? You guys can put that in the chat there. No, order does not matter. So can one person hold 2 positions at the same time, Strolling? Is that possible? So we have a 4-person committee here, which is true. Can we have one person hold 2 positions? Is that possible? They're picked randomly, but you're thinking about order in terms of people. I'm thinking order here, Strolling, not in terms of the people who are picked, because it's true, you're right, we are picking it randomly. True fact. But I'm talking about selecting not the people randomly, but where they go in the process. So order does matter here. So let me explain a little further. Once I pick, say I randomly pick a person here, Strolling. I randomly pick a person. Now that first person who's chosen is going to be the chairperson of this committee. Once I slot that person into the chairperson committee of the committee, then I cannot put that person into any other spot on the committee. So that person cannot be vice chair, that person cannot be a secretary, that person cannot be a treasurer. Okay, so that's why order matters here, because once you select that first person, that's the role that they're going to play. So order here does matter quite a bit because of what happens to the person after they're selected. So the order of the person, the randomness is fine, but again, because certain positions in certain order of how I select it, well, then order does matter at the end of the day. Now, if order matters here, how are we going to express picking 4 people from a 20-person committee? How should I do that here? Remember, there are 20 people total. Okay, very good. So 20p4, I agree with that. We're going to have 20 people in this, and we're going to permute 4 of them. Now, you're correct here, Strolling, of 20 factorial over 16 factorial. This is true. Okay, so again, if you do this out here, we're going to have this. We're going to have 20 minus 4. So I completely agree with you 100%. Alright, so we have 20 over 16 here. Again, factorial of each, just as it was written here. Again, you could do 20 times 19 times 18 times 17 times 16 factorial. So this is certainly plausible, divided by 16 factorial. Now, here's the issue with this. This could take a while to write out. Even I'll freely admit that, okay? So let's see if we can pare this down into an easier to do sort of thing. Okay, so how would we do that here? Actually, first of all, let's get an answer for this. Just go ahead and multiply this out, and then we'll see how to do it the short way. So 20 times 19 times 18 times 17. What's that going to be? So 20 times 19 times 18 times 17. 116,200? Is that right? Isn't 16,200? Yeah, I was gonna say, I'm like, hang on a second, seems a little off. Oh, that's okay. Don't worry about that. It happens. No big deal. Alright, 280 sounds correct. Alright. So 116,280. So what we can say is there's 116,280 ways to form this 4-person committee from a pool of 20 people. Fair. Now, let's say we want to replicate that answer. So if I say, okay, you know what? This is our final answer of 116,280. Okay, so we know what the final answer should be. Can we replicate it? That's the question. And the answer is yes, and in a very direct manner as well. So what I would like you to do now is I would like you guys in the chat to go ahead and take out a calculator. All right, once you have your calculator in front of you, go ahead and type done in the chat. So type done in the chat once you have your calculator in front of you. So that way we can go ahead and get started with this process here. So do a little bit of calculator stuff here. So please type done in the chat once you have your calculator in front of you. Bill, do you have your calculator there? We just asked that. Okay, everybody okay? Maybe Bill stepped out for a second. That's okay. All right. In any case, let's go ahead and take a look at how we can, again, get the same answer here of 116,000. Oh, okay, Bill's got it. Perfect. Okay. All right. So what we want to do here first on the calculator is we're going to go ahead and put it in exactly as you see here on the screen, like 20p4, but we have to set it up that way. So whether you have new school or old school calculator, you're going to do it the same way regardless. We're going to put the number 20 here to start with. So let's just put in the number 20. Okay, so just type in the number 20. That's perfectly fine. Now, I'm going to type this out here in the chat, so that way you'll see what to do next. So what you need to do is you need to hit the math key, and you need to go over to the PROB menu. So we're going to go to the math key here. You'll hit the left arrow, right arrow to go to the PROB menu. Okay, this little side menu right here. And we're going to select, specifically here in this case, we're going to select number 2, which is NPR, just exactly the notation that we have here for permutations. And hit enter. Okay. Oh, I picked the wrong one. Try that again. I thought I put it over that. That was stupid. All right, try that again. For some reason, I thought it was over NPR. All right. Now, if you have the old school calculator, that's perfectly fine. You're going to see this, so you'll see literally the letters written like this. If you see it written like this, again, this just does the nice little fancy schmancy formatting stuff for you, but really no difference. Again, we're going to put the number 4 here since we want to permute 4 people in this committee. For old school calculator users, this is what it will look like on your main screen. 20 NPR4. Okay. So it could look like mine, or it could look like what I posted there in the chat. All right. In any case, we'll go ahead and hit enter on that. And as we can see here, we get exactly the same amount that we just got from before, being 116,280. Okay. All right, so one more time. Type in the number 20. So scrolling one more time. Type in the number 20. Hit the math key. Scroll left to right over to the PROB menu. Go down to number 2 here, which is NPR. Hit enter. And then hit 4, because 4 is what we have here on the calculator. And then hit enter. All right. Any questions about that? Strolling, did you get that? Okay, cool. Did everybody get this answer here? Just type done in the chat if you got this same answer on your calculator. Make sure that everybody got the process right. Type done in the chat if you got this answer on your calculator. All right. Very good. All right. Good stuff. Okay. Any questions about that so far? Any questions? All right. Okay. Let's talk about the next part here then. we're going to talk about permutation's counterpart or complement, whichever way you want to call it. Again, it's opposite. It's opposite way. Permutation's opposite person here is going to be combinations. Okay, so let's talk about combinations here in the next question. So the way it works is basically what number 4. What is a combination? A combination is the number of arrangements of R things chosen from a pool of N things, just like a permutation, but in this case, order does not matter. So that's the big key thing here, is that order will absolutely not matter at the end of the day in terms of how we go about our process. All right? And we have a note, so we have here NCR, and typically as we say NCR here in probability or mathematics, is we say N choose R with the C for combinations. So C stands for combinations, but again, N choose R is typically what we see. It's N factorial divided by R factorial times N minus R factorial. Okay, and I did put a little note here is that repetition is not allowed. Now you're probably wondering, well, hold up a second here. What exactly do you mean by that? What does that mean? Okay, repetition is not allowed. I don't know what that means. Okay, let's do a practical example here, and I'll show you what I'm talking about. All right. So really quick here, let me at least ask you guys here, since there's not too many people in here. That's fine. How many people played the lotto before? How many people have played the lotto? You know, yes or no if you played the lotto before. Maybe you played Powerball or Mega Millions or a scratch off ticket or something. You have you guys played the lotto before? No, yes. Me? Chris is like, yes, I have. No, that's fine. It's fine if you haven't. That's fine. Which is perfectly understandable. Okay, so if you played the lotto, you know that, of course, you know, there's hundreds of millions of dollars. But, of course, the winning the jackpot, as you know, in a Powerball or, you know, Mega Millions game is pretty difficult. If, you know, nigh impossible odds in some cases. All right, now what we're going to look at here specifically in this particular example is we're going to look at the Powerball. You probably are wondering, how do you get the odds of winning the grand prize in the Powerball? Now, the grand prize in the Powerball currently sits at like $570 million. Okay, so let's say we are going to win the grand prize. What are the odds of winning that grand prize here? Now, let's talk about the rules here, though, of how we can actually make that happen. So the way Powerball works, at least the rules of Powerball that we have to follow, is that there's going to be 5 white balls, okay? And then 1 Powerball, which is red. Alright, so that's separate. So the Powerball is separate than that of the first 5 white balls. Now the Powerball here is labeled from 1 to 26. And then we have the 5 white balls here. The 5 white balls here are labeled from 1 to 69. Very nice. Alright. So we have all that. That's all well and good. Alright, so what we're looking here, let's take a look at this, and I'll show you what I mean here about using our combination stuff. So let me show you something here. Let's say I bought a ticket for Powerball. Okay, so I picked 5 numbers. Okay, let's say I randomly picked 5 numbers, alright? And in Powerball. And I picked the Powerball, of course, to go along with that. So I bought a ticket. I got some rows of numbers. It is what it is. Whatever. Alright. Now let's say I had, let's say there were different pulls for the Powerball. So we're picking 5 white balls out from a drum of 69 balls, right? And let's say these were the results that came out of these random draws, right? Okay, so I want you to take these group of numbers that you see here on the screen. Here's my question to all of you. Is 1, 2, 3, 4, 5 the first thing that you see here? So let's say 1, 2, 3, 4, 5. Is 1, 2, 3, 4, 5 the same as the next line down? 2, 1, 4, 5, 3 in this game of chance. Is 1, 2, 3, 4, 5 the same as 2, 1, 4, 5, 3? Is 1, 2, 3, 4, 5 the same as 3, 4, 1, 2, 5, that third line that you see here? Is 1, 2, 3, 4, 5 the same as 4, 2, 5, 1, 3? Yes or no? Within the context of this game of chance. So Bill says yes. All right, what else? What do other people think? Yes or no? Is 1, 2, 3, 4, 5 the same as the other three lines of numbers that you see below? All right, very good. The answer is definitely yes. 1, 2, 3, 4, 5 is exactly the same as 2, 1, 4, 5, 3, is exactly as 3, 4, 1, 2, 5, is exactly the same as 4, 2, 5, 1, 3. Okay, those are the same exact numbers. Those are the same 5 numbers, 1 through 5, just written in different order. So what does that mean? That means that in this case, when we're playing Lotto, on my ticket, it's written in numerical order. If you ever play Powerball, it's always written in numerical order. I'll show you a picture. Everything is always in numerical order. So I'm going to show you a sample Powerball ticket for just as a quick example here. So a sample Powerball ticket looks akin to where is it, like this. So here's a Powerball ticket. It looks like that. If you take a look at the ticket here closely, from this close-up, again, as you can see, all the numbers are written in numerical order. So all you're trying to do is match up the numbers here, and you don't care what order that they come in, as long as you match up the numbers appropriately to what's on your ticket, then you're going to go ahead and win a prize. Okay, hopefully the grand prize. All right? So, because all of you have said, and correctly so, that 1, 2, 3, 4, 5 is the same as everything that you see here, then what that means is that each one of these is the same representation. And what we want to do here specifically, let's talk about that for just a moment. What we want to do here specifically is we want to not count this 2 times. So that's one of the things that we don't want to do, is count this twice. Okay, so we don't want to count these guys here because these 3 are the same representation as 1, 2, 3, 4, 5. We only want to count 1, 2, 3, 4, 5 once, and then that's it. So what that indicates to us here, by logic, says that means that order does not matter. Doesn't matter how 1, 2, 3, 4, 5 is written, it's the same darn thing every time down, as you guys have correctly said. Does everybody understand that? Everybody see where I'm coming up with that? Any questions about that? Okay, good, good. All right. So, if I were to look at the number of combinations of, again, the 5 balls here, all right, if I were to look at the number of combinations of the 5 white balls here, then, welcome back, one. Then basically what I'm going to be looking at here is I'm going to be looking at 69. I'm going to do 69, choose 5, because we have 69 balls total overall, and we're going to choose 5 of them in which to pick our 5 numbers for our Powerball. And then on the other side, of course, Powerball, there's 26 Powerballs here, so that part doesn't matter too much. Here you go. We're going to multiply that by 26. Okay, so let's go ahead and see what we get here for the number of possible combinations for the Powerball here. So we're going to do this on our calculator together. 69, choose 5. We're going to multiply that by 26. Let's bust out our calculator here. So to get 69, choose 5 on your calculator, again, we're just going to put in the number 69 here. Okay. We're going to go ahead and hit the math key. We're going to go down to number 3 this time, which is NCR. So NCRC for combinations. So that's the only key difference here is we're going to hit number 3, hit enter. We're going to hit 5. Again, don't forget, you do want to hit if you do have this formatting here, by the way, you want to go ahead and hit the right arrow here so you get to the main line here, and then hit times 26. Okay. And we'll go ahead and enter. So we have 292,201,338 different combinations in the Powerball. So your odds of winning in the Powerball, your probability of winning the grand prize is 1 out of 292,201,338, which is a extremely low percentage. All right, any questions about that? All right, let me ask you guys one more thing. Let's go ahead and have you guys type done in the chat if you were able to replicate this answer. Make sure that we type done in the chat to replicate this answer. Make sure you guys got that right on the calculator. That way you'll know what to do when you see questions like these. All right. Very good. So far, so good. Okay. Let's move on here then to the next question, if there are no questions. All right. Okay, so let's take a good look here at, actually, that one wasn't that great. I don't know why I did that problem go around. Oh, nope. Give me just a second, I'm trying to get to the next page. Where the next page is, I don't know. Come on, next page. Alright, hang on a second, folks. For some reason, this does not want to cooperate. So, because the next problem I want to show you is on the page. Okay. Okay, let's go back. Grab the e-text. I swear this book is so finicky to access. Ugh, come on. Sorry, guys. Apologies. Oh, come on, book. Please load. Would be great. Okay, here we go. That's so weird. Alright. Okay. All right, let's take a good look here at this next one here. We're going to do number all right, sorry about that. Sorry for the slight delay. All right, now I got the page I want. All right, we're going to do number 61 here next. Okay, so let's do 61. All right. So 61 says selecting a jury. So this time we're going to find some probabilities associated with this. All right, so actually I'll put this on the other side. All right, but let's go ahead and read this off here while I move this over. All right, so 61, selecting a jury. The grade appeal process at a university requires that a jury be structured by selecting 5 individuals randomly from a pool of 8 students and 10 faculty. Letter A. What is the probability of selecting a jury of all students? Okay, so let's do that. Let's go ahead and write down our situation at hand. So we have, again, we need 5 people. We need 5 for the jury. So we're given 10 faculty instead 8 students. Okay, and again, letter A, probability that they're all students. Okay, so the way we're going to break this down specifically is I'll guide you through this first one here. The way it's going to work out is we're going to have 2 parts here. Okay, let's talk about those 2 parts. Okay, so the 2 parts here is on the top part here is the number of ways that we can have an all-student jury. Okay, so number of ways for all-student jury. Okay, for all 5 students. Okay. And then specifically, what are we dividing by? Well, we're trying to find the total number of ways, okay, to pick 5. All right. So let's go over each part here. Okay. Now, in this instance, let's answer this question first because we did discuss both topics. Does order matter in this process of selecting a jury? Does order matter? Yes or no? So order matters here in selecting this this particular process. So let me put this into context here. If I had a jury of Tom, Mary, and Bob, is that the same jury as Mary, Bob, and Tom? So if I have those 3 people, then they're the same. So basically, if I have Tom, Mary, and Bob, and Mary, Tom, and Bob are the same thing, well then, in that case, guys, order does not matter. Because again, we can flip the number of names around, but it's still the same jury at the end of the day because it's still the same 5 people. So I want you to understand that it's like, okay, we talk about order mattering or not mattering. In this case, order does not matter. Okay, as long as you have those same 5 people and those are the same 5 names, no matter which way you write those 5 names, it's still the same jury no matter what. It doesn't matter what order I pick first, second, third, or fourth, or fifth. That doesn't matter. Okay? That doesn't matter whatsoever. So, order does not matter. So we're going to use combinations here in this case. All right. Now, if I'm going to pick 5 students, I totally understand that. Order does get confused with repetition. This is true. We don't want repeats. We do not want repeats. So again, that's where order doesn't matter because we don't want to count repeats again. Again, if the best way to kind of think about this, Sanla, is like saying a race would be a permutation. Okay, so like a race would be a permutation because it does matter who comes first, second, third, and so on and so forth in a race. Order definitely matters in a race, okay? But if you're just choosing, okay, if you're just choosing, that means that, again, that will be, again, a combination, okay? If you're just choosing with, again, no order, all right? So if you have people in particular positions, then yes, it's going to be a permutation. But if you're just randomly choosing with no rhyme or reason, then it's like, okay, you know, something akin to that if you want to liken it that way. I hope that reduces the amount of confusion about picking the difference between a permutation and a combination. Now let's take a look here at this. We have the number of ways for all 5 students. All 5, excuse me, all 5 people happen to be students here as part of this jury pool or jury thing. All right. Anyway, so what's the number of ways we can pick all 5? Let's answer this question here. How many students do we have in the pool of people? How many students do we have in the pool of people? How many students we got overall? Okay, we got 8 students, right? I totally agree, right? So overall, we have a big, not 18 here. Careful, just looking at the number of students here specifically, Sanla. So I have 8 students in the pool. I have 18 total. This is true. I agree with you, Sanla, on that. There's 18 total people, but just amongst the 18 people, how many of them are students? Well, there are 8 of them. Okay, no, that's fine. It's fine. No big deal. But since we're trying to find the number of ways for all 5 of them to be students, we're going to do 8. Since we have 8 students here in the pool, we're going to choose 5 of them. Okay, so we're going to have 8 choose 5. All right, so that's the number of ways for all 5 of those people to be selected as part of the jury to be students. So 8 choose 5. So out of the 8 students, we pick 5 of them. Fair enough. Now we think of the total number of ways to choose 5 people. So this is the overall big picture aspect. Okay? So now, how many total people do we have in the pool of people? So now how many total people do we have in the pool of people? Right. That's correct. We have a total of 18 people. So just like Sanla said and just like you guys are saying, we have a total of 18 people overall in the pool. And then out of those 18 people, we're choosing 5 of them. So this is just basically overall, I'm just randomly choosing 5 out of the total pool of 18 people. So that's going to figure out how many ways overall that we can select a committee, or in this case, a jury of 5 people. So that's why I have down here an 18 choose 5. Now you could do this as 2 separate calculations, or on your graphing calculator, you can put it as one big one. So, for example here, on your calculator, again, you can just put parentheses if you feel comfortable with that. You put 8, we'll go to PROB, go to choose 5, hit that right arrow there, close that off. Divide it by 18, and we have choose, PROB, go down to 3. And we're going to hit choose 5 here. All right. And I'm going to go ahead and hit enter. So in this case here, you could figure these out as 2 separate things or just all as a decimal at the same time. In this case here, 0.0065 is to get a jury of all students out of the 5. All right. Any questions about that one so far? I'm going to look at the other side of things, but... Any questions so far? Hopefully that isn't too hard. Alright. Okay. Now, what I would like you to do here is to go ahead, and we're going to go ahead and use this as a nice little springboard for the next example. And hopefully you'll be getting this, hopefully by this example you can see the pattern that we're going to use here primarily. So the next example, part B, asks, what is the probability of selecting a jury of all faculty? So the probability of selecting a jury of all faculty. So all 5 are faculty. So let's talk about the expression. Well, the expression on the bottom here should be pretty easy. Anybody tell me here, what should I have in the bottom here? What's the total number of ways to choose 5 again? What should I have in the bottom here? What's the number of ways to choose 5 overall? 18 choose 5, okay. That's right, Maritza. Alright, very nice. So we know that it has to be out of 18 choose 5, right? That has to be true. So that's fair. Alright, completely fair. Alright, no problem there. Now let's look at the top there. Let's look at the top there. Now we want to pick all 5 people to be faculty members as part of this jury. So all 5 are faculty. Whoa, okay. Alright. Very good. That is correct. Very nice. Okay. So, in order for us to pick our 5, we have to select from our pool of 10 faculty overall. That's right. So we're going to have 10, and from the 10, we're going to choose 5 of them. So 10 choose 5. Alright, so now I would like you guys to plug that into your calculator. So 10 choose 5, divided by 18 choose 5, and if you have an answer for me ready, I will certainly take that off your hands. Anybody have a decimal answer? I'll give you guys a... I know it takes a little time to enter in. Okay, so 0.0294. Good. All right. So far, so good. Excellent job. All right. Any questions so far about that? Any questions? No? Okay. All right. I'm going to go ahead and do... Okay. So let's take a good look here at letter C. Now, letter C is going to be the trickiest one of the bunch, okay? So I'm not going to lie here. This one's a bit tricky, but let's see if we can, guys, get through this here. You guys have been pretty much plowing through a lot of these problems here, which is good to see. Trust me on that. Very good to see. So let's just take a gander here. See if we can get through this one here. So this is the probability. What is the probability of selecting a jury of 2 students and 3 faculty? So 2 students and 3 faculty. So 2 students and 3 faculty. Now, one thing that we can take to the bank here is we already know how many total that we need here. So what we can take to the bank is already what we did in the previous 2 problems. We know it has to be over 18 choose 5, all right? So that part there, guys, just like it was before in the previous 2 parts, no problem. The real issue comes down to is, of course, the first part here, which is, of course, expressing 2 students and 3 faculty. How do you think we could figure that out? The number of ways to get 2 students and 3 faculty to be part of this this jury here. How could we express 2 students and 3 faculty? What do you think we could do here? Let's start off with something easy, okay? Let's do this, okay? Probably the toughest part of this is this part here. Let's start off with 2 students here. How could I express the number of combinations of selecting 2 students? Why don't you guys answer that? The number of combinations of choosing 2 students. Find the probability from 1 student. No, I don't want to do that. Not just 1 student here. We're gonna need to find the number of combinations. That's close, Strolling. Not quite though. We can't put 2 choose 5. The first number always has to be bigger than the second number. So that's not possible. I have to pick 2 students. 5 choose 2. That's a good guess there, Maritza, but not quite either. Again, we want to have 5 people overall. This part is true. But don't forget the pool of people that we're working with. So if we're picking 2 students, what's our pool of students again? How many students do we have total in this case? Think about what you did for part A. Same deal. Okay, 8 choose 2. Right, it would be 8 there. So I agree, 8 choose 2. All right, so let's at least go with that. Okay, so let's start with that there. 8 choose 2. All right, fine. All right. Now, let's look at 3 faculty here, everybody. Now I know that's 28 there, Sanla, but I'm gonna do something with that here in just a moment. Let's go with 3 faculty. How can I get 3 faculty? How can I choose 3 faculty from my pool of people? What's that gonna be? What's that gonna be from my pool? Okay. 10 choose 3. All right. So we're looking at this as, to be fair, we're looking at this as kind of 2 separate guys, and that is perfectly acceptable. That's exactly how I actually want you to do it. Look at it as 2 separate guys here. That's not a problem. All right. So let's look at how we do this here. So we have 10. We have 10 choose 3. Okay, so far so good. Now, here's the trick behind this, guys. Here's the trick. And this is the one thing to keep in mind here, where I hope that you don't get confused as part of this process here, is kind of what goes in the middle here. So what goes in the middle here specifically between 8 choose 2 and 10 choose 3 is we don't want to add those number of combinations together. What we're going to do is we're going to use the general multiplication where we're going to multiply those 2 things together. Okay, so we are going to multiply. So be very careful about this, not adding, multiply. Okay, so note here is to multiply. Not add. So that is exactly how we're going to find the number of combinations. Is we're going to take 8 choose 2, multiply that by 10 choose 3, and then take whatever that result is, we're going to divide that by 18 choose 5. Now let's go ahead and do that on the calculator here. All right. So if you have the calculator here, probably the easiest way to do this on the calculator is just to go ahead and just separate them out appropriately. Okay, or again, you could put this underneath the same set of parentheses. So you have 8, math, arrow B, go to choose 2, and then you hit times, and then 10, choose 3, Okay, we can close those parentheses and divide by 18 math. Yes. Choose 5. Okay. Does anybody have an answer for me here? If right before I hit enter, anybody got an answer for me here, decimal wise, of course. What's our probability here for this problem? 0.3922. Okay. Alright, so we'll go ahead and hit enter on this, and that is correct. Alright, very nice. Very nicely done, everybody. Very nicely done. Alright. Are there any questions about this example here? I hope that now you got combinations down and probabilities to see where we're kind of putting that together there in that example. Any questions about that one? Got one more example to do, but hopefully that makes things... No! Emphatically, Strolling's like, no. No way. Okay, got it. I understand, Strolling. He's like, I want to slap you in the face. Like, let's slap the teacher in the face, just say no. I'm like, okay. You didn't have to slap me, I totally understood the first time. Alright. Okay. Alright, now let's look at the last example here. It's okay. I'm just fooling with you, Strolling. I'm just fooling with you. I know. Like, most things people do are just accidents. It's fine. I just happen to joke around a ton. That's all. Don't worry. Don't worry. It takes a lot. Like, honestly speaking, guys, it takes a lot for me to be sincerely, like, mad at you guys. No, trust me. I don't get angry too often at all. No, actually, too often. That's the least. People type in caps. You're like, my God, it's not a big deal. I think it's funny. So, all right, number 5. Let's look at number 5. What are the number of permutations with non-distinct items? So let's talk about what this means here. So, basically, this is like non-distinct items. Essentially, I'll just demonstrate it in the example that we have listed here. So, the way it goes is that the number of permutations of n objects of which you have a of one kind, b of a second kind, all the way up to z of a kth kind, is given by n factorial divided by a factorial b times b factorial times ... times z factorial, where n is equal to a plus b plus all the way up to z. So, the example that I have here is, what does non-distinct items mean? Well, I used a flag example here. So it says, let's say I have a flag of 3 colors. Now, if they're non-distinct items, essentially all the flags are the same dimension, okay? Let's say all the flags that I'm going to use in this example are the same dimension, all right? The only difference between the flags is not how they're manufactured, but it's just the color of the flags themselves. All right, so they're non-distinct outside of the actual color of the flags. So there's only one thing separating those particular objects at the end of the day. So let's say we're trying to make an arrangement with these flags. So let's say the flag here can have different arrangements using colors. Say we have 5 green flags, 3 red flags, and 7 blue flags. Okay? How many arrangements are possible of 15 flags? So, again, 5 plus 3 plus 7 will be the 15. Okay, just to justify where we're coming up with 15 flags. Alright, so 5 green plus 3 red plus 7 blue is 15 flags overall. Alright, and the way we get our answer here, how many possible arrangements, is we take the 15 factorial, that's for all 15 flags. Alright, and we divide that by 5 factorial times 3 factorial times 7 factorial, which, if you do that out, is equal to 360,360. Okay, so this is if you're running into a situation where things are pretty indistinguishable The key here being this line right here, which says non-distinct items, okay? So non-distinct items. They're pretty much, each item is indistinguishable outside of one characteristic that makes it unique compared to the other. Okay, so in this case, it happened to be the color of the flag that made it unique compared to the other flag of the same dimension and type. Okay. And then and again, the number always has to equal the number you're permuting. So again, if this was 6, I'd have 6 plus 3 plus 7, so this would be 16 flags. I would have to save 16 flags instead of 15 flags, so just depends what that total is at the end of the day. And there you go. You got yourself a winner chicken dinner. Alrighty. Good beans. Alright, any questions about non-distinct items here? Hello, Dylan. How we doing? You're up late once again. It's like 1 in the morning over there in Liverpool. Burger actually for dinner. You go out to Nando's or something. No questions? Very good. How's school treating you, Dylan? I hope it's treating you well. I think you started, right? So, or I think you did start, so. Okay, now, just to let you know, I did ask the first class, and I'll ask you guys the same thing. Section 5.6 here, this is all Section 5.5 that we did here today. Section 5.6 is basically a review section over everything in Chapter 5. Now, I'm going to ask you guys the same thing. Would you guys like me to do a review of Chapter 5? We'll do that for next class. If you'd like me to go over particular questions you'd like me to talk about, I can certainly do that here. The first class had decided for me to go ahead and do a review, but it's only fair if I ask you the same question as well. If you'd like me to do a little bit extra review here over Chapter 5 if you felt confused at certain parts, and I'll be more than happy to go over questions, and then we can move on to Chapter 6 once we go ahead and do that, or if you'd like me to start with Chapter 6, we could do that as well. But what would you guys like to do here? I'll put a little poll here. You guys can decide whichever. Alright, so... So you ordered pizza, it never came. How does your pizza never come? So the pizza never came, so you ordered burgers and chips. How does your pizza never come? You don't have to pay for it, do you? Unless you paid over the phone. Well, I don't know if you pay over the phone or not, but how does that even work? You order pizza, but your pizza never comes. That's terrible. Just what kind of service do you have out there for pizza delivery? It's like here in the States, that's sacrilege, Dylan. Now, I know it's delivery, but that's sacrilege out here. You cannot have no delivery of pizza. That is just like bad manners all around. It's bad manners. You cannot have that happen. I'm gonna be honest with you, buddy. Like, no joke. It's terrible, man. How do you not deliver, bro? Really? So jokes. Okay, let's see what you guys have to say here. Alright, all of you said review? Okay. So that's what we're going to do here. That's what we're going to do here, guys. We're going to go ahead and do review here of Chapter 5. So there's, again, questions in Section 5.6, which does cover review here for this chapter. So that's what we're going to do. So no worries. That is what is on the docket here for next time. Alright, so we're going to come back here on Thursday at the same time, same place. Dylan, we can talk on Discord. So you give me like a couple minutes. I'll talk to you on my Discord. Okay. All right, guys. I want to thank you all. You gotta head to bed. I thought you were having burgers and chips. All right. All right. In any case, if you're heading to bed, then have a good night there, Dylan. All right. I want to thank everybody. Quick eat. That's fair. Um, I want to thank everybody who came out here to the you too, Dylan. You have yourself a wonderful evening. I want to thank everybody who came out to the chat. Dylan, of course, included. You're always welcome here, Dylan. At any time, you are a absolute gem of a man and a friend of the channel. Um, thank you all very much. You guys are absolutely fantastic. And I will see you all same time, same place here on Thursday, okay? Thursday, same time, same place. Everyone, have yourself an absolutely wonderful evening. We'll continue doing review here for Chapter 5 for next time. Have yourself a wonderful night, all right? Take care of yourselves, everybody. And as always, everybody, stay safe, stay healthy, but most importantly, stay safe, all right? We'll see you Thursday, all right? Take care. Have a great one, everybody. Thank you. Thank you. Thank you, guys. Thank you, guys. Take care of yourselves. We'll see you later. All right, everybody. Take care. All right. Bye. Bye, everybody. Have a great one. Have a good night.